Hello friends, welcome back to Measure Theory lecture series. I am Sahil Singh Mandari. This is our lecture number 6. In this lecture, we are going to see some properties on measure. Okay, so we have done the measure in the last lecture. So let x m be measurable space and define mu be measure on xm. Okay. Yeah. So properties are as follows. First one is let E1 to En belongs to n, okay, where n belongs to natural number, and all the Ei's are disjoint, okay. That means all Ej intersection Ei equal to empty for all Ij belongs to 1 to n. Okay, then this property says that the union of all the Ei's I running from 1 to n is same as sigma mu of I running from 1 to n. Okay. So in the last lecture we have seen that when we define the measure, its property was that the union of all these disjoint infinite sets was same as the summation of their individual measures, right? Here if we will take this sequence E1 to En, and after that we will take just all these sets to be phi, then again we will reach to the same conclusion. Then from the property itself we can see that this is true. Okay, let me remind you that mu of all the Ei's I running from 1 to infinity was sigma mu of I running from 1 to infinity. Okay, if Ei's were the Ei's belongs to M and all the Ei's were disjoint, okay, then this was true. Now, after a certain stage, like in this, I have defined some number n. So after the n, if I will take all the sets to be empty, en plus 2, so on to be empty, then this property holds. Okay, so we have proved the first one. Now let's see second property. Property number 2. If EF belongs to M and E is subset of F, then mu of E is less than or equal to mu of F. Okay, so this is another property, we will prove it. Its proof is, so till now we have the properties for measure on disjoint sets, right? So let's make some disjoint sets here. So let E and F, but not in E. These two are disjoint sets, right? Why? Because this is the set E and this is the set in which all the elements belongs to F but not in E. Therefore, these two sets are disjoint sets. That means that their intersection is empty, right? So we can apply the property of measure on these two sets such that mu of E union F but not in E is same as sigma, or we can say sum of these two individual measure mu of E plus mu of E F but not in E. Okay, so we can see this is nothing but F, right? Because F was the subset of, means E was the subset of F. So from here we can conclude mu of F equal to mu of E plus mu of F but not in E. Okay, so let's recall that mu was a function from M, that was sigma algebra generated by some subset of x to 0 to infinity. That means mu will always give us a positive real number. Okay, that's why this implies that this number will be greater than or equal to 0. Okay, so if this is, even if it is non-empty f but not in E, f removed E, it's also possible that mu of this will be 0. Okay, and this is the positive number, therefore from here we will get relation mu of f is greater than or equal to mu of. Okay, so we are done with the property number 2. So let's see property number 3. This property says, let Ej be a sequence in M such that Ej contained in Ej plus 1. Okay, that means this is monotonically increasing sequence. Okay, for all j belongs to natural number. Then mu of union of all these Ej, j running from 1 to infinity, will be equal to limit j tends to infinity mu of Ej. Okay, so actually this property looking obvious because all these union will just contain in the infinite j, right, in the Ej for infinite j. So therefore this will be equal to this one, but now we will prove it logically. Let's prove it. Okay, so again we have to make some disjoint sets. So let's make some disjoint sets as fj equal to Ej but not in Ej minus 1. Okay, for j greater than or equal to 2. Okay, and let's define f1 to be equal to e1. So let's observe that all the fi's are disjoint sets, right? Now all the fi's are disjoint, because if we will pick any two of the fi's, then we can see that like in f2 we have e2 removed e1, and f3 we have e3 removed e2. So here e2 is not there, and in this e2 is there, right? So their intersection is empty. So this is true for all the fi's. Therefore now we can apply the property of measure here, that mu union of all the fi's will be equal to sigma mu of fi I running from 1 to infinity. Okay, and also observe that if we will see the union of all the fi's I running from 1 to k, then it will be simply ek, right? Why? Because what was our fi? Fi was simply ei but removed ei minus 1. So if we will take union of all these, like f1 union f2 union f3 so on till fk, then from here fk minus 1 we will have ek minus 1 removed ek minus 2, right? And in this fk we have ek removed ek minus 1. So from here we have ek minus 1 there, and from the previous one we have ek minus 2 there. Therefore we will have the union just to be ek. Okay, so we can write mu of union of fi I running from 1 to k equal to mu of sigma mu of fi I running from 1 to k. Why we can write this? we can write this using property number 1, right? If we have finite number of disjoint sets, then we can write it as this thing. Therefore we can write finite number of, we have here finite number of disjoint sets, and we can write it as this one. Okay, so this implies mu of ek equal to sigma, like f1 plus f2 so on plus fk. Okay, from here we can conclude itself that mu of union all the ei's I running from 1 to infinity will be nothing but limit of this summation. Now here, okay, uh, if we will sum this to the infinity, I running from 1 to infinity, this will be equal to this one, right? So what we can see here is, if mu of ek is this one, like sum of all these fi's, so mu of union of I running from 1 to infinity will be simply as limit j tends to infinity mu of ej. Okay, so this we have proved. Okay, so another thing is, till now we have proved this for the disjoint finite disjoint sets, and the union of these can be written as this thing, their individual mu summation. Now we will generalize this case. Okay, what do I mean by generalize? I mean that if I will take any two sets E and F belongs to M, and we will take their random sets, means E intersection F cannot be empty, means these E and F cannot be disjoint sets. So now let's measure these, let's define some measure for these two sets. So what will be mu of E union F in this case? Okay, so its proof is, we have a tool that we can play with the disjoint sets, right? So we will make some disjoint sets here. Let disjoint sets to be E removed F, F removed E, and E intersection F. Okay, so all these sets are disjoint sets, and their union will be just E union F. Okay, so union of all these disjoint sets will be E union F. E removed F union F removed E union E intersection F will be equal to E union F. Now apply the definition of measure on these. We will get mu of E union F equal to sum of all these individual measures, that is mu of E but not in F plus mu of F but not in E plus mu of E intersection F. Okay, yeah. So now we will observe that we can write E as E removed F plus restore these things from E intersection F. Okay, and these both sets are disjoint sets, therefore we can define mu of E as mu of E removed F plus mu of E intersection F. Okay, so from here we can see, we can write mu of E removed F as mu of E minus mu of E intersection F. Okay, so just substituting this value of mu of E removed F into our original equation, we will get mu of E union F equal to mu of E minus mu of E intersection F plus mu of F but removed E plus mu of E intersection F. Okay, Similarly, we will compute mu of f but not in E, and we will get it as mu of E minus mu of E intersection F plus mu of F minus mu of E intersection F plus mu of E intersection F. Okay. From here we can conclude that mu of E union F is equal to mu of E plus mu of F minus mu of E intersection F. Okay, so this was our end result. Hope you understand, and thank you for watching this video.